So as we look through the operations of real numbers, we're going to look at warm-up here. Cindy and Victor are playing a math game, and the winner here must get the row of the same type of number and justify, that means explain, how the numbers are alike. Cindy said she won because she was able to get 3 rational numbers on the diagonal. However, Victor said he won because he was able to get 3 positive numbers in a column. Can both players say they won for different reasons? And like we said earlier, the key thing right here is type. What does the word type mean? And the answer is, it's actually pretty vague. Because you might say, oh, look, you could actually argue, look, they all have a curve. Look, that 3 has a curve, that 0 has a curve, and there's an itty-bitty curve there. Now, that's a silly definition, but technically, you would be right. They all have a curve, okay? But it turns out probably every numbers have curves except for 1s and 7s. So that one would be almost too vague. But you said, but I define type as curve. Okay, right? So, but in this case, Cindy defined type as rational. In other words, what group of number, what subset of real numbers is it? So she was looking at rational, and let's recall, what does rational mean? So on the number line, a rational number is a number that can be written as a fraction, so it can be a whole number, a fraction, or a decimal. If the decimal ends or the decimal repeats, then, so there's a pattern, then those are rational numbers. So let's see, did Cindy get rational numbers here? Yes, this is a decimal that ends, this is a fraction, and this is a whole number, which can be written as a fraction. So she's good to go. And then the other one, Victor simply said, I want positive numbers. I want positive numbers. And as we look, it's true, they're all positive. We have positive 1.3, positive radical 10, and positive pi. So the short answer here is yes. Yes, they can win for different reasons because type is undefined. Because type is undefined. How about say not clearly defined? I'll say that. Clearly defined. So it's almost subjective. A person could, oh, type, I can make it a curve. I can say there's a 1 in it, right? Something like that. So we just need to be more specific. So first, a set of numbers is a group of objects, and it's often in math going to be numbers. An element, sorry, there's no S there, of a set is called the object. So for example, right here, 4 is an object in this set. And then we use these squiggle parentheses whenever we're identifying a set. So for example, A here. A is the name of the set. This right here is its name, the name of the set. And I do apologize, when I first made this, everything was as it should have been. So, but for some reason the formatting went off. A here should be italicized. I made that absurdly oblique. But you know how italicized means it like lines, it goes slightly to the side like that, like B there, and slightly like that. So technically these should all be italicized. Something happened to my formatting when I went from Google Docs to printing. So in future I'll make sure that it's accurate. Okay. So this is the set. What is this if we were to describe it? Oh, it's the set of numbers from 1 to 10. Set of whole numbers from 1 to 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's a set. Okay. Now, a subset is anything that you can take out of that. So if I just grabbed all the even numbers, 2, 4, 6, 8, and 10, B is a subset of A. Any number of elements from that group. So here, this is called the subset, and you could also even give it more of a specific name. It has a name B, and you could just say it's the even numbers from A. The even numbers from A. So B is a subset of A. More specifically, we're talking about the even numbers from A. Notice that C, the subset C, is a subset, 5 and 10. And if you wanted to describe this subset, you could say, oh, these are the multiples of 5 from A. So, to clarify here, we have D is defined as, and then of course we use the bracket symbol to mean a set or a group, in this case of numbers, and then I listed all the odd numbers. Officially, you don't have to list them in order, but it actually makes sense quite a bit. And notice it says the odd numbers. If it had said D as some odd numbers, you could have just chosen the first 2 or 3, or the last 2, or just some random ones inside. But it did say the, so that means the collection of all of them. And this would be F is the multiples of 3 as a subset of A. There we go. Okay, the next skill that we're going to look at is recognizing that when you are given a set of numbers, you might need to put them in order. So if you're given these numbers, 4 over 11, or 40 over 11, the square root of 324 divided by 36, and the square root of 10. So how can we order them from least to greatest? So as we look at this one, what we need to do is convert everything to the same form. Now, it turns out that decimal is probably the fastest conversion. And we're just going to use our calculator for each one of these. So let's take 40 divided by 11 to get 3. 40 divided by 11 is approximately, see that symbol right there? That's an equal sign with a squiggle. That means approximately equal to, because I'm not going to write the entire number down. If I did, it would take forever. So I'm just going to say approximately 3.63 or 64. Next, the square root of 324 over 36. Both of these right here, we notice, are perfect squares. If you forgot what that means that when you take the square root, you get a whole number. So for example, the square root of 4 is 2, so 4 is a perfect square. Right there. All right, so when I take the square root of 324, I get 18. The square root of 36 is 6, and I'm going to change my symbol here to exactly equal. And then, of course, I can see that reduces to 3. Next, square root of 10. We can actually estimate that just in our head. I know that the square root of 9 is 3. So the square root of 10 has to be just slightly bigger than that. So if I were to estimate the square root of 10 as approximately 3.1, that's probably good. I'm going to check with a calculator real quick just to see what I get there. Square root of 10 gives me 3.16. So my guess, my educated guess, was actually pretty spot on. Okay, now we're not done. Now I'm going to order them from least to greatest using my information here. So because my radical 10 is 3.1-ish, this fraction here was 3, so that's even smaller, and then this one seems to be the largest, 40 over 11. So I'm going to write it out, and I'm going to use the original numbers. Okay, so I'm going to actually write using these numbers. So the first number is the square root of 324 over 36. Since it asked me to write it from least to greatest, I can just write it as a list. Then the next one is the square root of 10. And then the next one is 40 over 11. I'm going to box or circle that because I'm communicating that I'm done. That is my answer. Over here is just my thought process, my work, my scratch work. That's fine. But when you are finished, whether it's on a test, a quiz, or an assignment, make sure to box or circle your answer so that I don't have to guess what's what. Now that we have a graph as an alternate way of looking at things, we can make the list here. Square root of 121 over 25, comma, radical 5, comma, 2.25. And box or circle it there. The last thing that we're going to look at actually is going to seem familiar because we've already seen something like this. And this is just us getting the idea of how numbers are dealt with. For example, before we said an even plus an even was still even, right? Well, what about these two here? What about the sum of two integers? If you have an integer plus an integer, what do you get? And what about the product of two integers? Go ahead and make a conjecture there. Go. Numbers. I'm going to test that. The sum of two integers, let's see, 3 and 12. When I add those together, I get 15. Oh, 15. What kind of number is 15? So it's not about odd and even, because I could have chosen two evens. When I add those together, I get 16, etc. Integers can be negative as well, which means I can add a positive and a negative. So I could have tried a couple different ones, like I did here. I'd throw some negatives in there, maybe some bigger numbers. When we add two integers together, we'll always get an integer, no matter what. The product of two integers seems to be an integer. And just to test that out, 3 times 8 is 24. 6 times negative 5, both of those are integers. We get negative 30. So we're still in the integers. I'm not getting anything fractionized. I'm not getting any decimalization to occur there. All right. So what do we think about this? The sum of two rational numbers is what? So you might have an idea, an inkling of what to write down. But before we do that, let's just try a few things. So for example, if I had 1/10 plus 7/10, these are both rational and fraction numbers, so they're not whole numbers. In this case, I get 8/10, and I can reduce that to be 4/5. So notice, I start with a rational, I add another rational, and I still get a rational. Okay? Another example, and we did this one already, but we could say something like this, 1/2 plus 1/2. Notice what that gets me. 2 halves, which is 1. The question is this a rational number? But is that a rational number? Good. So we see that both of these so far, the 4/5, the 1, both of them are rational so far. We could even try another one out there, because rational numbers don't have to be fractions. They can be decimals as well. So I could even toss that out, a few decimals, right? So 0.35 plus 1.22, okay? Add those together to get 1.57. Okay, the decimals give me decimals, but not always. I could have added 0.5 plus 0.5 and still gone. So it seems that each one of these, no matter what, gives me another rational number. Another rational number. The question is, can I trust my conjecture? So this is what's called a conjecture. It is an educated guess based on a pattern. We saw a pattern, and we see these fractions equal fractions when we add them. This fraction's a whole number, but it's still irrational. The decimals add to a decimal, but it's still rational. So here's my conjecture. Here's my guess as to what it might be. But we haven't proved it. I can't say this for sure yet. Why is this, trying a few examples, why is this not a good strategy to prove something? Because the list of examples never ever end. I can add 1/10 to 7/10, 1 plus to 8/10, 1/10 to 4/5, 1/10 to 1/2, 1/2, and there's an infinite number of fractions, infinite number of decimals, infinite number of negatives. I can never make the list complete. So we have to use not examples. We have to use not examples. Instead, we're going to do a proof using variables. About some variables, I'm going to say that A, B, C, and D are real numbers. In fact, I'm going to be more specific. I'm going to say that they are integers. When I say they're integers, I'm not dealing with fractions or decimals at all. Okay, so here we have a bunch of integers, only whole numbers and their negatives, okay? Which means I can make each one of these into a fraction. For example, A over B plus C over D. Each one of these is rational – because it's an integer divided by an integer. Each one of these is rational. You might have to take my word for the next part because it requires us to think about fractions. But how do I combine these? Can I just combine them across? When I'm adding fractions, what's the key thing about adding fractions? I need a common denominator here. All right, so I'm going to kind of go fast through this. If you need to take this video and back up a little bit, that's fine. But let me just show you how a common denominator can be found here. This guy has a d, and this one doesn't. So if I multiply this guy by d here, but also by the top, d divided by d is 1, which means it doesn't change the value, just changes the form. Same thing over here. This one has a b, this one doesn't, which means if I take that b and multiply it in the numerator and denominator, this is what I now get. In the numerator, I get a times d over bd plus b times c over bd. Now that I have a common denominator, the numerators can combine. AD plus BC, the AD here plus the BC there, all over the common denominator BD. Now, this looks ugly, but we're actually done. This is the proof. Let's explain. Now we need to use some words to figure out why. Up there we saw that the product of any two integers is an integer, right? Which means if a and d are integers, together this is an integer. And so is this, an integer. And so is this down here. It's an integer. We also know that when we add two integers together, which is now what this says up here, AD plus BC is an integer plus an integer, which means the numerator is also an integer. Ha! So in the end, you get this. In the numerator, you have an integer. In the denominator, you have a different integer. So by definition, an integer divided by an integer is rational. All right, your turn here. I would like you to do, here, the product of two rational numbers. Take a guess at what you might be, try a few examples, and together we'll walk through a proof. So our hypothesis, and remember, our hypothesis or our conjecture or our guess to what should be filled in here doesn't have to be written first. Let's try some examples here. So we're just multiplying. In fact, so 1/3 times 1/2. Those are both rational numbers. I get 1/6. Oh, rational times rational is rational. Let me try another one. 2/3 times -3/2. That gives me -1. I went from rational to rational to whole. Oh, but that's still irrational because it can be written as a fraction. So my examples here, it seems as though I'm still going to write the word rational down. Seems to still be rational. So let us see about proofs. Let's construct some, using integers, let's construct some rational numbers. A, B, C, and D are integers. So I'm going to create some rational numbers and multiply them together. So our first one, A over B. And I'm going to say times, because I'm doing product, C over D. AC over BD. Remember that multiplying fractions is less complicated than adding fractions. So all we do is multiply straight across. But what do we know about the product of two integers? That puppy is an integer. Y tú también. And the one down below is an integer. Híjole. So in the end here, we get an integer divided by an integer, and that is the very definition of rational number.